think they can stay in bed, right? Single slit diffraction. Write down this title somewhere in your notes.
Okay, I'm writing it.
Well, since I can't hear anything, at some point we should just like introduce a very random question and then just pretend like we know how to solve it.
Yeah, and then when they come in, I'll start the quiz, right?
Yeah.
Amazing.
Single slit diffraction and modulation of double slit by That's what we're going to talk about right now. So your double slit, you move over until the path difference is lambda, right? And that's going to look something like, if I draw this. Well, no, we won't do that first, sorry. Do that first. So if you have a barrier like this, let's say, I'm going to make it big because it's just easier to see. That. So these two are slits. And the waves come along, right? You're going to have the waves go out and you're going to have a bright spot in the middle, and then at some angle you're going to have another bright spot, right? And that's because, let's draw it like this. I'm going to put in this triangle that's 90 degrees. Stayed on the top or the bottom? Oh, did we hit play?
Yeah, we hit
Yeah, we're
record.
recording.
Yeah, theta's going to be on the bottom, right, Edward? Because you're moving like this, so as you move like that, you move like this. And so theta is going to be here for this sideways triangle. Yes? Okay. When this is the path difference, yeah? Between our 2 points of diffracted light. So when we get over to where this path difference equals lambda, this is the sine theta. Yes? And d being the distance between the slits. Okay.
We should come up with like a
You should
really
like-
hard question.
You should open the door for like 3 seconds and then close it on them.
Should I just pull this out? No talking, come in. No talking.
Study math.
Okay. The path difference here, when it becomes lambda, you get a maximum, right? So, when this is d sine theta, and when that path difference equals lambda, you get a maximum for double slit. What does a maximum look like on the screen?
Bright spot.
The bright spot, right? Now, that's all double slit. So when you change this theta, you move some angle. When those two rays are in the middle, you get a bright spot because they're constructive interferably. They're interfering constructively. And when you move over lambda, once you get to the next crest, so this path difference is lambda, you get another bright spot. That's your second maximum. Now, something interesting happens. If we draw this again, I'll do it over here. Can that see me over here?
Yeah,
Yes.
but don't go too far.
How about I go like
No, it has like pretty much the whole room.
No, everything's in there.
Oh,
Yeah.
I just have to.
everything's in there?
Yeah.
Everything.
Pretty much.
Yeah.
Okay.
Like even the far end, just like up to the L. I can see the calc over down here.
So draw this again, but this time leave the center barrier out. This is now a single slit, not a double slit. Something interesting happens. There was a guy by the name of Christian Huygens. Can I write over here?
Yes.
And he came up with Huygens' principle. Huygens' principle says that a beam of light is not a single beam with edges, but actually, instead of having, if I draw a beam of light, I'll do it in red. If you're like, yeah, here's my beam of light, and it's all, but it's all light. Huygens said that this beam is actually made up of a whole bunch of small wavelets. Thank you, Carl. So he said, instead of having one beam that's diffracting out, you have a whole bunch of different little wavelets. So you have one here, one here, one here. Here. All those beams are diffracting outward. So instead of just having two, so if this is our single slit, and we draw the same angle theta, like that, hitting the screen there, and we'll do the same triangle, there is a difference. So if that's our triangle, and this is the opening of the single slit, that's my theta. We're gonna get a different result if this path difference equals lambda. We don't get a bright spot, we get a dark spot. Why is this different than this? Path difference is the same, but you get a different result. If I take this middle barrier out, that maximum, that bright spot that's here, will turn to a dark spot here.
Is it because if you have the slit, then only waves that are lambda apart can go through and interfere, whereas those ones you can have like a wave halfway through and then it cancels out?
Golf clap for Carter. Golf clap. If you have just these two, Carter's right. You're gonna have crest and trough, and then you have this one lambda, and so you're starting here and you're starting here, and those are gonna line up at the end. But with this one, you've got no barrier in the middle. So what is my average path difference for all of these? Is the path difference lambda for every wavelet? No. What's the average?
Lambda over 2.
Lambda over 2. Right here between these two, if they're really close together, it's almost 0. From here to the end is lambda, but from here to the middle is half lambda, and from the middle to the end is half lambda. And so your average path difference here becomes lambda over 2. And so that's why you get a dark spot. And so you can have d sine theta for a double slit, you get a maximum, but for a single slit, you get a minimum. And that's, of course, going to be dark. Does that make sense so far? So for this situation, D is the width between from slit to slit, right? But if you're looking at just one single slit with no barrier between, that D is the width of the slit. Mark, with me? Make sense? Okay. Rohan, you agree? Now let me ask you this. These are each individual slits, yes? Do they have width? Edward just rolled his eyes back in his head. He's like, they do, I know. These slits do have some width, right? So they're going to be affected by this phenomenon, even while they're interacting with each other. Okay. Can I erase this all? We got a video. Oh, by the way, if somebody can come up with a way to take a video from my phone or someone else's phone and get it easily onto the classroom. Yeah.
Oh, easily onto the classroom.
Well, just so some way for you guys to get it.
Well, you
can just
put it
upload
into a
it.
drive,
Yeah.
and then just share a folder in a drive.
So I found that if I just take the video, it's like it doesn't work very well. So I made a YouTube link, but then it's hard to get the YouTube link onto the drive. Actually, it's not so easy. But anyway, we'll talk about that later. Maybe somebody can help me do that. Okay, if you're looking at the screen, but we're gonna turn our screen flat now. So give yourself some room above. And if you shoot a double slit diffraction pattern, what are you gonna have in the middle? Constructive. You're gonna see a bright spot in the middle, right? And then you guys remember this? I showed you with the laser pointer, right?
Yeah.
And what else did you see? Little spots out here, right? So this is your maximum, and so this is going to be a graph of intensity. You have this central bright spot, and then you have the next spots. Do you remember, were they as bright as the central one, or were they less bright?
Less bright.
Should we look again?
Yes.
Carlos, like, if you want to. Okay, let's do it. Just so you can see it.
No, you don't need it to increase. You literally have a line in this trace. Oh, it's not.
So that's the spot. There's your spot. And then you put the grading over it. And you see, if I go like this, you can see that it's,
Why is it?
why is what?
I thought I saw 4, but one of them's just like the actual screen.
Oh, it might be a reflection.
No, like it's the one. There's a laser through the screen, and there's the 3 being reflected off the screen. So it looks like 4, but it's 3.
Yeah, okay. Are the outside spots the same brightness or less? Definitely less, right? Can't see the outside ones. It'd be nice if we could see the outside ones too. Oh, do you see the 5th one there?
Yeah.
So this is the first maximum, and the outside there, if you can see it, is the kind of third maximum.
Well, isn't it because like the intensity has to do with distance, and then you're adding more distance? Or is it more?
You mean like why is it less bright?
Yeah, like.
It's not the distance. If I shoot this from back here, it's no less bright. It might get a little bit less resolved. It's not the distance. What it is, so your brightness would be like this, and this outside one would be like that. So we'll do this on this side too. Yeah, this side. This is the diffraction pattern due to double slit, but each of those slits are also affected by this because they have a width as well. Now their width is obviously smaller than the space between the slits, so it's a smaller d, right? So if d is smaller, what's going to happen to theta? Is the lambda changing? No, we got the same color light. Radine? If this gets smaller, theta must get bigger, right? So it's not as close as this, your next maximum. It has to be way further out. So, but you're gonna see the same type of pattern, except the maximum for a single slit is gonna be farther out. So you'll actually see that this will come along and it'll try to have another maximum, but each of the single slits is dead. It's dark. So you get nothing here. And then you'll have like a maximum here and it'll go like that. And the same thing over here. It'll be like, alright, no, that's dead. So that's something you need to understand and need to be able to explain. Is why are these points less bright as you go further out? And it's because each individual slit, as you move that theta, your individual slit is getting less and less bright because your path difference is going from the same to closer and closer to lambda. And when it hits lambda, then you're gonna have a dark spot. Now that's going to happen at a big theta for a single slit because the D is small, so the theta has to be big. But it is going to get to that minimum out here. And so each beam is getting darker and darker and darker. But then they still interact with each other. So you still get a bright spot, but each beam is darker, and so you get not as bright of a bright spot. Does that make sense? Sort of. Okay. That's the lesson. I have some problems for you to work on today. I have started marking your tests. I don't know if you want them or not. No.
I like a nice
No.
weekend.
You want a nice weekend?
Yes.
You don't want to think about it?
Yeah.